Hey, welcome back, you crazy cats. Today we're going to be learning about potential and kinetic energy. You're going to learn about the equations for potential and kinetic energy. We're going to learn how to differentiate between the two forms. We're going to learn how it's conserved, how you can identify internal energy, and how you can identify mechanical energy. Energy is the ability to do work. Kinetic energy is energy of motion. And potential energy is stored energy. We have several different forms, and these are not the only forms of stored energy, but these are ones that we'll work with quite a bit. We have gravitational, which we have an equation for, which is potential energy is mass times gravity times height. That's why we call it gravitational. And then elastic, or I can't think of what the variable, and that would there be for potential energy is 1/2 kx squared. You also have chemical potential energy off the top of my head. So there's lots of different other forms. And then the equation, which I didn't discuss for kinetic energy, was 1/2 mv squared. And this is when something is moving. The units for energy are joules. All right, it's a lady's best friend. The way we get joules is we take a Newton times a meter. If you remember from the other day that work was energy, and we said it was force, which is newtons, and distance, which is meters. So we had force times distance, which was how we got joules. And if you want, in class we can go and I can show you how they get joules from kinetic energy and how they get it from potential energy, but we'll talk about that in class if you want. Why? Well, look at gravitational potential energy and work. Like I said, we'll talk about that in class. Okay, let's talk about what's called the work energy theorem, and this deals with kinetic energy. This relationship is called the work energy theorem, and what we get here is the work is equal to the change in kinetic energy. The delta, this triangle means delta, or means change in kinetic energy. So what they're showing us down here is if we apply, this object had this initial kinetic energy. All right, you could say it was 0 if that makes it easy for you, because then the math is real easy. So, but it had this initial kinetic energy, and we apply a force for some distance, and we're saying it's frictionless. All right, that's important. So we apply a force for a distance. That means we're doing work. Force times distance. And when we apply a force over a distance, it's going to cause this velocity to change, because a force, when applied to a mass, causes it to accelerate. So this mass is going to accelerate or have a new velocity. So that means it's got more kinetic energy than what it started off with. Well, what we're saying here is that the change in this kinetic energy, let's say this was 0, and over here it was 100. So the change was 100 joules of kinetic energy. That was the change. Where did it come from? It came from the work that was done. The force times the distance has to be equal to that change in kinetic energy, as long as this is frictionless. That is also true when it comes to a change in potential energy. There has to be some type of work that was done to have caused that change in potential energy as well. Okay, let's talk about that variable potential energy here now. All right, we can therefore define the potential energy of a spring. Note that as the displacement is squared, this expression is applicable for both compressed and stretched springs. In this case, what they're saying is, because no matter which way you move it, because we're squaring it, the negative is going to cancel out, that it doesn't matter if we're talking about compressing it or stretching it. So the potential energy, and they're using U, I'm usually going to just use potential energy, the PE still for this, is equal to 1/2 kx squared. Let's talk about gravitational potential energy. In this case, they're telling us that there was this can that had mass, gravity is pulling on it, force is applied to it. Well, let me backtrack. Originally it was sitting down here on the table in the center of the mass here. All right, work is done on this can. There's a force, all right, there's a force that we're saying here that's applied for some distance, call it delta y. So this force is applied for a distance. Well, force times distance is work. Well, that work has to be equal to the change in potential energy, and that right there would be mg times this delta y, or a lot of times we'll just simply refer to that as h. I can see that they're using u here. Again, I'm going to use PE quite often for potential energy. All right, we're going to do some simple practice problems here dealing with potential energy and kinetic energy. A 2.5 kilogram rocket is shot off. It achieves a speed of 120 meters per second in 0.35 seconds. How much force did the rocket create? Well, the force would be mass times acceleration. We know the mass, but what we don't know is the acceleration. Well, a rocket starts off with initial speed of 0, and they're telling us that it achieves a speed of 120 meters per second, and it gives us a time of 0.35 seconds. So I'm going to use my kinematic equation here to find out what that acceleration is. We get 120 equals 0 plus acceleration of 0.35. Divide both sides by 0.35. Now I've rounded off, but we got an acceleration of 343 meters per second squared. So to find this force, I'm going to take the mass of 2.5 and times it by 343. So that force turns out to be 858 newtons. How high did it go in that 0.35 seconds? Well, they're wanting to know YF. I've got a time of 0.35, so I'm thinking YF equals YI plus VIT plus 1/2 8 squared. The reason I'm using acceleration is it's the engine that's accelerating it, not gravity. So I put the acceleration in from the engine. I put the time in there. We're going to get a height here then of 21 meters. So some of you are thinking, oh my word, I didn't realize we were going to do all this kinematic equation stuff. Well, right now we kind of have to. How much work was done in the first 0.35 seconds? Work equals force times distance. The force in this case is 858. The distance is 21 meters. So we're going to get an answer for work here. 21 times 858 gives us 18,018 joules, because work is energy. All right, so that's how much work was done. Well, calculate its kinetic energy at the 0.35 second mark. Kinetic energy, finally doing something with today, right? 1/2 mv squared. We're going to take 1/2 times the mass of 2.5 times its velocity, which is 120. I left off the squared, so I went ahead and put the squared on there. The kinetic energy is 18,000 joules. All right. All of that kinetic energy for number 4 will turn into potential energy. So how much higher is it going to go? Because what's happening now is all of this energy is due to its speed, but now the engine has stopped firing. So it's going to start losing speed because gravity is pulling on it. So as it loses speed, it's losing kinetic energy. But we can't lose kinetic energy. We'll talk more, or can't lose energy. It can only transform, and we'll talk more about that in days to come. But all this kinetic energy is going to go into the form of potential energy. So I'm going to say 18,000 equals the mass of 2.5 times 9.8 times the height. So when we do this and put it in a calculator, we get an additional height of 734 meters. So that's how much higher it's going to go. Okay, let's do a practice problem here with energy in a spring. So right now I'm thinking potential energy equals 1/2 kx squared. Pogo stick is designed so that a 20 kilogram girl dropping from a height of 0.4 meters will compress the spring by 12 centimeters. Well, that's going to be 0.12 meters. What must be the constant of the spring? Well, all of her gravitational potential energy will go into the spring. So she's dropping from a height of 0.4 meters. So I'm going to find out what her gravitational potential energy was first. The mass is 20 kilograms. Gravity is 9.8. Oh, yes, and her height is 0.4. Her potential energy is 78.4 joules. Now, I know we haven't talked a lot about it, but again, energy can't be created, lost, or destroyed. So we have this thing called conservation of energy, and we're going to use that concept here. And we're going to say that all of her gravitational potential energy is going to go into the potential energy of the spring when she compresses it. So when she falls, the spring is going to be compressed. And then it's going to have this amount of potential energy, or this ability to shoot the girl back up. So now I'm going to put this over here for potential energy. 1/2, I don't know K, and X is 0.12 squared. So what must be the constant of the spring? That's our K value here. That's telling us how strong the spring is. And we'll talk about that here in a second. I really haven't talked much about that yet. All right, so what we get here then is 10,888.9 newtons per meter. Now, that tells us the strength of this. So if we were to take a string and stretch this, or a spring, sorry. So here's my spring. And we were to stretch it, or do the opposite, compress it. In this case, the spring was compressed, but it's the same math. If I was able to stretch this spring a meter, all right, for every meter we stretch it, it's going to gain this ability or this desire to want to snap back. And it's going to have a certain amount of force when it does snap back. And that force would be equal to 10,888.9 newtons per meter for this particular spring. There's springs like in your pens. Those springs don't have a lot of strength, so they wouldn't be nearly as strong as what this one was. Well, tomorrow in class, we're going to have to talk about internal energy. We're going to have to talk a little bit more about conservation of energy. And then the last thing we're going to talk about is mechanical energy. So we still got quite a few things to talk about tomorrow in class. But for right now, hopefully these are a lot of these things, except for maybe these three right here. Hopefully you can discuss the first two pretty well when we come into class. I'll catch you on the flip side.